Welcome to lecture number 40. In the last lecture, we have discussed about the total internal reflection geometry to achieve a very tiny observation volume, and we are also discussing about this confocal geometry to create the small observation volume. In the confocal geometry, I was showing you this diagram with this animation, that if I have this excitation light and this is my lens, so this molecule is actually diffusing, and when this molecule will enter this observation volume, it will going to show the fluorescence, right, and when it will go out, right, then we will not going to see the fluorescence. So this is given here, right. You see, in this case, this is my excitation laser beam, right. When it will reach this sample position, let me define these samples are present throughout. Let us say this is your sample position. Starting from here, everywhere is your sample, everywhere is your sample, and when, so all are sample, right, all are sample. So if you just follow this excitation light, I will just take this which color is this blue one. So I will just take this same color and I will redraw this excitation light, please follow. So the excitation light is coming like this way, this way, this way, and it is exciting throughout. This is the other side of this excitation light beam, and then it will excite throughout. That means whatever the molecules are present within this shaded region, let me shade it nicely. So this shaded region will be excited, whole shaded region will be excited. But obviously this volume is much more, right, it is not like a femtoliter, 1 femtoliter. So to get this 1 femtoliter, I must restrict my observation to some part of that, the tiniest part in the width of this excitation beam, as I told you in the last class, will be somewhere in the focal plane. That is the tiniest one, right, if you remember I showed you, right. So this is the spot size, right, and so the observation volume, if I can restrict around this region, then that will be the tiniest, right. So if you restrict your observation around this region, then the size, the volume will be more than this, that is for sure. So I need to do something over here, so that, right, although the molecules which are present here or here or here or here, everywhere the molecule will give fluorescence, but I am not going to detect the fluorescence from everywhere. I am going to detect the fluorescence only from a specific position, right, within this observation volume. How to achieve that? That is the question, right. It is simple, that if you just put a pinhole over here, right, I just put a pinhole. Now let me erase all those things and you follow this line. As I told you that this blue one is your excitation, so everywhere excited, that means the molecules which are present at this position, that is also going to be excited, the molecule which is present at this position, that will also be excited, and the molecule which is present at this position, that will also going to be excited. Now you follow this line, the molecules which are present below the focal plane, right, after you putting the pinhole, let us say first you follow the line, the molecules which are present at the focal plane. So if you follow this line with a basic knowledge of your optics, you follow and you see this red actually passing through this pinhole and reaching the detector. That means the fluorescence which is originating from this position, this focal plane, actually is reaching the detector, because this pinhole position is over here, right. Now keeping this pinhole position same, I mean, do not move it now, keep the pinhole position same, keeping this pinhole position same. Now if you follow the line, the ray diagram of this light originating from this particular position, you see, the follow it here, it will be something like this, and then it will go like this way, and it is blocked, this part is blocked over, this part is blocked over there, right. So, it cannot reach the detector. Now, if you consider this point, right, if the fluorescence originates from this particular point, you follow this line, what you are going to see, it is now blocked at this position and this is now blocked at this position. So, the placing a pinhole at this position ensures me that the fluorescence which is originating very near to the focal plane only will be passed through this pinhole, and that light only going to be detected by this detector. That same figure or that same concept I have displayed over here. In this case, you see here that this is your focal plane. So, when the signal is originating, this is your focal plane, right, here this plane. When the signal is originating from, let us say, here at this position, it is not passing through this pinhole, it is blocked. When the signal is originating from this position, it is not passing through this pinhole, it is blocked over here, is blocked over here, is blocked over here. But when the signal is originating from this focal plane, this signal is passing through, right, see, signal is passing through this pinhole, right, and this is called this confocal geometry. That means, it is very simple. You have objective, you have this lens, and you are exciting, you can excite the sample throughout, but just by putting this pinhole, you can actually restrict your observation volume. Now, I will go back to my this animation. Now, you see here, once you excite, your molecule will start moving, because the molecular motions is random, right, it is a Brownian motion. So, once it enter over here, then this signal is actually passing through this pinhole, where with this pinhole and will reaching the detector. But when the signal is like this, when the molecule is present over here, then that signal is blocked. When the molecule is present over here, then the signal is also blocked over here. So, you will going to get the signal only when the molecule is present within this volume, and the height of this will be guided by the width of this pinhole, right. There is a direct relationship from this width of the pinhole and height. And if you now consider that is a Gaussian shaped of this laser beam, then with using some mathematics, you can actually calculate the volume of this observation, right. So, it is called the detection volume or observation volume, this region or observation volume. So, that is it. If I can achieve this observation volume, then I can see the single molecule. When the molecule will present inside this observation volume, then it is visible. When the molecule is present outside, if the molecule is present here, it will be excited, it will going to give you fluorescence, but it is not visible because of this pinhole, right. Once the molecule is here, obviously it will give the fluorescence, then only it is visible. If the molecule is present here, right, then it will not going to fluoresce. If the molecule is present here, it will fluoresce, but it is not visible. If the molecule is present here, it will not going to fluoresce. So, I can restrict my observation and I can achieve this femtoliter type of observation volume. Now, consider that you have some matrix, let me draw this matrix over here. You have some matrix and you have all the molecules are present, right, throughout this matrix. Let us say this is your matrix. Let us say it is a polymer matrix, and in this polymer matrix the molecules are present, right, and you have sufficiently dilute condition, so that the this between the two molecules are far apart. One molecule is here, another molecule is here, like this molecules are present. But as this is a solid matrix, this is in this plane, right, in this plane, and if you just take a cross section, probably we will see one molecule here, another molecule here, another molecule here, another molecule here, 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 random distribution like this, right. So, now if you want to image how the molecules are distributed in this matrix, what you are going to do? You will just put this slab polymer slab having all these molecules embedded inside in a confocal setup, right. In the confocal setup, you have this observation volume. The observation volume is having certain width and certain height, right. The width is guided by this diffraction limited focusing, which is the approximately half of this wavelength, right. So, you will get a spot size like this way, and then you will get a depth because of the presence of pinhole. Let us say this is your resolution. So, if you scan, what you are going to see, either this layer of this molecule, this is layer 1, right, let us say, and obviously below that there will be another layer, right. Below to this layer there will be another layer, like this is a layer by layer. So, depending on which one you are actually so this is a layer by layer thing. So, depending on the height of this observation volume to this sample, you will be able to see one layer. Now, if you look at one of this layer, what you will going to see? You will going to see these molecules, because you will going to scan, right, this observation volume. The observation volume is here, then you scan either in xy plane, you will scan in the xy direction. So, then you will going to image everything. So, after you scan whole thing at a particular plane out of this slab, obviously we will going to see that one fluoropore is present over here, another is over here, another is present over here. It is random, I do not know, I am just writing, I am just drawing it. Probably you will going to see such kind of image, one is present over here. Here please note that this spot size, right, is in the order of 200-300 micron, which depends on the excitation wavelength, the light wavelength of the light you are using to get the spot size, and that is called the Abbe diffraction limit. And in this case, the spot size will be almost the half of this wavelength, right. If you are using 400 nanometer light for this excitation, the spot size will be around 200 nanometer. Obviously, the molecules, right, they are not like 200 nanometer, they are about 1 nanometer, but still you will get a bigger spot size because of this diffraction limited focusing. But no problem, if the intensity of this spot is same as this spot, is same as this spot, is same as this spot, that means I can conclude that each spot you will have a similar number of molecule, and in this case the number of is 1, right, because you have taken a reasonably diluted condition. So, number will going to be equal to 1. But if you look at this real image of this, the first thing what you are going to see is this. These are the molecules, right. What you are going to see is that some of them are light, some of them are dark. I mean, it means that intensity is more, and for some intensity is even more. So, there is some distribution in the intensity. Does it mean that more than one molecule is present? As I have taken a sufficiently dilute concentration, then it is unlikely that in one place 2 molecules will be there, in the other place none of them is there, right, for this even distribution of this molecule in this particular medium, considering that there is no specific interaction and all the location in this matrix are equally probable for this type of molecule which is present in the system. The reason behind such kind of difference in the fluorescence intensity from each of the spot may be because of the different orientation of this molecule. As I said earlier during our discussion on fluorescence anisotropy, that the direction of the polarization of this excitation light, right, will excite selectively or preferentially those molecules whose transition moments are parallel to the electric field of this excitation line, right. So, it is possible that for this molecule the excitation is more favorable because its transition moment is oriented in parallelly to the electric field of the excitation line. In this case it is not, right, it is possible. So, in this case the different molecules are not aligned in a similar fashion, right. Sometime if you take this kind of image, you would also see such kind of feature. Like this is your, this is not a full circle, this is a half circle, right. Let us say this is the full circle, this is again full circle, this is full, and let us say this is half, right. You will also see such kind of image, right. So, I am just considering intensities are same just for the time being, you will going to see. So, what is the reason for this, right, because you are going to scan your laser, right, throughout this matrix. Here when you are scanning like this. Let me change the color quickly. You are scanning like this, you are going from here to here, you are coming like this and then like this and then like this and then like this, right. Like this you are scanning and you are creating this image starting from here, here and then like this. Like this, right. It means that when you are seeing here this fluorescence is on, but when you are coming back it is off. That is, the half circle is fluorescent, not the full circle, right. That means if I sit on a particular fluorophore and keep on monitoring the fluorescence intensity, right, it must show the on and off behavior, and exactly the same when you sit on a particular fluorophore in this matrix, right. You just focus on this one, right, just focus on this one and monitor how the fluorescence intensity is changing with time, right. Then if you plot this fluorescence intensity with time, what you are going to see is a kind of fluctuation. The fluorescence intensity is more and it is like this, and then it become like this and stay sometime from here, and then again it will increase, it will stay like this way, and then again it will come back and stay like this, and ultimately it will never come back, it is 0, and this is called the blinking of fluorescence. This is basically because of this conversion of the molecule from the singlet state to the triplet state. When the molecule will go to the triplet state, obviously it will take some time to come back from the singlet state, and fluorescence is only from the singlet state that we already discussed, right. In the triplet state, phosphorescence is typically quenched by this different quencher present typically by the oxygen molecule dissolved in this your system. So, we are not going to see the phosphorescence at the room temperature. So, once the molecule will go to the triplet state, it needs to come back, and that takes time, and that is called my off state. So, here is my off state and here is my on state and so on. But if you keep on excite the molecule, right, many times, then the molecule may destroy, and it is a very common feature, and this part here the molecule will never come back to give you fluorescence. That means the molecule is destroyed, and this is called the photo bleaching. Right. Okay, so these are the typical behavior of this molecular fluorescence, but single molecule fluorescence. Now, if you just sit over on a particular molecule, right, and you just keep on monitoring until and unless this molecule will go bad, that means photo bleached, right, then you can get several information about this molecule. For example, you will going to see the single molecule spectra, you will be able to see single molecule lifetime, you can see the application of rate in the single molecular level, and many other application is possible. But I would like to tell you one important application which is not in the solid matrix, but in the solution state, right. And if this is my observation volume, now you have a clear idea about this observation volume, right. When the molecule will come within this observation volume is my molecular trajectory. Here the molecule is non-fluorescent. The molecule fluorescence will be detected only when it is present within this observation volume. Throughout this path, right, throughout this path, the molecular fluorescence will be detected, and the molecule, right, will take some time to cross this observation volume. If the molecule is entering from this side and taking such kind of path, then this fluorescence will be on for longer time than this. If the molecule is coming from this side and exits from this side, then the fluorescence is on for a shorter time, right. So here the fluorescence is on for a short time, here the fluorescence is on for this time, and in this case the fluorescence is on for a much longer time. If the molecule will come like this way, then the fluorescence is on for this time, right. So if you now monitor the fluorescence, right, as a function of time, then what you are going to see, you will see there is no fluorescence. This is the fluorescence intensity, this Ft is the fluorescence intensity from the observation volume, right. So in this case the fluorescence intensity is on for when it is present like this. So fluorescence intensity is on, and then fluorescence intensity off. That means none of these molecules are present here. If none of them is present, although the molecule here is getting excited, because your excitation light is like this, right, it is excited, but you will get the fluorescence only when this is not excited, right. This is excited, but you will only get the fluorescence only when it is present within this observation volume. That height is determined by the width of the pinhole, the size of the pinhole, right. So then again, once the molecule will enter, it will be like this, and then like this, like this, like this, and so on, right. Now so there will be fluorescence intensity fluctuation, right. I can simply write this as intensity fluctuation. Now you consider the diffusion of this molecule in and out of this observation volume is slow, right. Then this self similarity of this fluorescence fluctuation will be more, because the molecule is present for the longer time within this observation volume, the fluorescence is on, and if it fluctuates rapidly, then the self similarity of this fluorescence fluctuation will be less. So that depends on how quickly the molecule is coming in and going in and coming out of this observation volume, right. So if I consider a short time period, for very short time period, right, obviously there will be lot of self similarity, right. If I consider this fluctuation now and this fluctuation after a very small time, that means the fluctuation should be very similar, right. Then there is a lot of self similarity. But if I now consider this fluctuation and same fluctuation after certain time, after some time, then the self similarity will be lost. But if these fluctuation widths are more, right, if this is on for longer time, let us say if it is on for this time, this whole time region, then it is off, and then it is on for this whole time region, then even for this case compared to the black one, in this case after a certain time that self similarity will remain very high, right, and that self similarity is expressed by this fluorescence autocorrelation function, and which is denoted as g tau and defined as fluorescence intensity at time t, fluorescence intensity at time t plus tau average divided by average fluorescence intensity square. Like now, if you change this tau value, right. So, the fluorescence intensity at time t and time t plus tau will be very similar if the tau equal to 0. That means, it is the fluctuation will have very similar fluctuation, because it is same, right, ft and ft is same. But when I change this tau from 1 tau to 2 tau, and some time if I give 1 microsecond, 2 microsecond, 10 microsecond, then the self similarity will be lost, right, and you will get a lower value of g tau. So, g tau will start from a high value, and it will ultimately will going to be 0 when the value of tau is very large. And in this case, this decay of this g tau should be related to the how quickly the molecule is passing through this observation volume. In other words, it should be related with the how this what is the size of this fluoropore. If the size of the fluoropore is big, then it will take some time to pass through this observation volume, and that can be correlated easily. If the viscosity of the medium is high, then the molecule will pass through, right, this observation volume the longer time period, and it will be seen in such kind of g tau. I will just show you this typical plot of this g tau. As you can see here, the g tau is plotted against this obviously tau, right. This is tau is in the microsecond. So, here is your 1 microsecond, 2 microsecond, 3 like that, 10 microsecond, 100 microsecond, 1000 microsecond, and so on. So, you see this g tau value is very high, is about 1, right, is about 1 over here. That means, there is a lot of similarity between the ft and ft plus tau at 1 microsecond, right. But as that tau value is changing, it is going to be 0, but there is no self similarity, right, at 10 to the power 3. Now, if whatever I said, I expressed this in mathematics, right, then it should be related with the diffusion time. And if I show you that particular equation, now you see this g tau is related to this tau d, that how fast this molecule is passing through this absorption volume, and this is guided by this particular equation, right, and where n is the number of molecules present in this observation volume. Right. And you see that these experimental data, those circles, these experimental data are now fitted with this equation to get this value of tau d. Once you know the value of tau d from Stokes-Einstein relationship, you will be able to calculate what is the volume of this molecule if you know the viscosity and temperature, and vice versa. So, this is a very important application in single molecule fluorescence, and this particular experiment is known as fluorescence correlation spectroscopy. Okay, and is in short form it is known as FCS. Okay, so we will finish here as our time is up. Thank you very much.